it had an application though, but I think the link.
Morning.
Hello, good morning.
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 Good morning. So let's wait a couple of minutes for maybe, and then we can start. So for today we have G. I don't know if I'm pronouncing your name correctly. G is
Jay,
fine.
yeah. Jay.
Okay. And then and we have Tom Popovici. So you know, like during the last couple of weeks, we have a lot of talks that have been inspirational or very inspiring, and that give us kind of the overview of where we're going. But today's talks are very technical. So these are the people that are actually doing the groundwork. So it's going to be quite interesting. So we're gonna start with G because he has he is gonna have to leave earlier today. So we're gonna start with him. So he's gonna have 30 minutes. Let's say 20-25 minutes, so we have some time for questions. And then we're gonna have Tom that is going to talk about density functional theory and the other accelerator that he has been working on. Some of the work that Tom has been working on is the one that John Schaff introduced to us. So some of those algorithms such as DFT that requires also fast Fourier transform and TSQR and other things. So that's going to be also quite interesting.
Hey, Patricia.
Yes.
Can you also introduce Professor Diego Llanos?
Of course. So I would say, Diego.
Hello.
I mean,
yeah, so I think
yourself.
I'm going to pass it on to the professor, but I think this is Raghu. Good to see you on in this meeting, Professor Diego. So Patricia, if you remember, had presented some good work by Professor Diego and his team around HPC kernels on FPGAs, and a lot of the work that they have done we could learn from and see how it applies to the model architectures for HPCs. So he has kindly agreed to at least attend one today, maybe some more, and maybe he can present his work. But I'm glad. So I think just want to pass it on to you, Professor.
Okay, thank you very much. It's a pleasure for me to attend this meeting. And as you said, I would prefer to stay quiet and listen and learn some things before try to describe our research lines.
So what we can do, if you would be interested, we can have a separate meeting where we kind of pitch our idea and what we're trying to do here in the work stream, and see if that would be of interest. I don't know if Raghu already gave you some information or
no.
Okay.
Unfortunately, no. This is my first meeting, and I'm trying to understand what are you doing right now.
So let's do that. So let's try to have a separate, I mean, if you have time and if you would agree, let's have a separate meeting where we can maybe show you the slides that we have, the introductory slides, and so you understand what is the modularity that we're looking for.
Mm-hmm.
Okay, so I think we can start now. So G, I think you can take it from here, and then we're very excited to have you. Thank you so much for agreeing to talk to us.
Yeah, sure. Thank you. Can you guys see my screen?
Yeah, we can see your screen. Mm-hmm.
Okay. I cannot find. Okay. Good morning, everyone. My name is Jay. Currently, I am a postdoc research associate at Texas Tech. It is my honor to be invited to give this talk today. So basically, this talk summarized the methodology we used for collecting data from the promoter, and we use the metrics and the data collected and presented in our ISC paper. So hopefully this talk will give you some ideas about how we do the data collection and analyze the data to have some insights, results of the promoter. So let's get started. So this diagram gives an overview of the format methodology. So on the left side, we have CPU nodes and GPU nodes of the promoter cluster. And on these nodes, we have LDMS and also DCGM for GPU nodes to get the performance metrics of each monitored nodes. And in the middle of the figure, we are showing that these monitoring metrics are managed in two kinds of formats: the CSV files and also the Victoria metrics. So these metrics collected from these nodes are actually node level performance metrics. To get more insights of the data, we also combined the data we get from this Slurm workload manager, and we basically merge the node level performance metrics with the job metadata to get the job level performance metrics. And these metrics are saved in Parquet files, and then analyze this data using Python and Jupyter Notebook. So I will go deeper into the LDMS and also the DCGM monitoring tools in our later slides. So LDMS stands from Lightweight Distributed Metric Service. It is developed and maintained by the Open Grid Computing and Sandia National Labs. So it is open sourced, and you can get the source code through this link. And similarly, DCGM is also open sourced and is developed and maintained by NVIDIA. Here's a link to this tool. So for the LDMS, actually it has three different kinds of modules, as showing on the right side. So the first one is the sampler module. So basically it runs on each monitored nodes, and it run one or more sampling plugins to periodically get data from the operating systems. And the aggregator acts as the kind of a middleware between the nodes and also the storage, and it collects data from the samplers or other aggregators, and then these aggregated metrics will be processed by the storage plugin. So it provides different formats for the storage, including the MySQL database or CSV files. So I also list these documentation and the tutorials here. So for those who are interested in playing with this tool, you can go to this website. And also the DCGM, similar to the LDMS, but it is specific for the GPU nodes. And the DCGM daemon on the GPU nodes will interface with these GPU hardware and also the software layers, such as the GPU drivers, the management library, and the code toolkit to get these performance metrics in real time. And DCGM also provides a tool called NV Host Engine. It acts similarly to the aggregator in LDMS, and we can configure a central management node to aggregate, to run these NV host engine tool to aggregate metrics from multiple remote GPUs. However, DCGM do not have the storage plugin, which means we have to develop our own tools to process these collected metrics. But fortunately, it is not very hard. We may use several ways, such as the scripting, or we just use these DCGM Python API to develop our customized integration tool. So again, here is the documentation for this DCGM tool. So as for the Promata settings, basically the samplers are collected at an interval of 10 seconds as of July last summer, actually. So these performance metrics are, like I mentioned, are actually saved in CSV files and in the Victoria metric database. So here I list two examples of these metrics we've collected. On the left side is the memory-free metrics. As we can see, we have producer name, which is the node ID, and the timestamp of the data that collected. And we have the metric readings for this memory-free column. And on the right side is for the GPU utilization, as each node have several GPUs. So we also have a GPU ID column in this data. So for each CSV, it is actually can be as large as like 500 gigabytes. It's a very, very large, since it combines the metrics collected from several, probably like hundreds of nodes. And like this diagram shows the interface for getting the metrics through the Victoria metrics database. Actually, it is much easier for query the performance metrics. And if we want to get metrics from the CSV files, it actually relies on the file system hierarchy to get a specific metrics during a specific time, which is not user-friendly. So the user has to understand the hierarchy and get the corresponding metrics. And these Victoria metrics, we can just use the API service to export this data into CSV files. And this is the pipeline for the extract, translate, and also the loading the data into our data analysis tools. So basically, we developed a tool called VMSS account, and it accepts 4 parameters: the start time, end time, that is the time range of interested data, and also we have to specify the sampler and the metric we want to use. So the VMSS account will query the Victoria metrics to get the job level data, and it calls the S account command tool provided by the Slurm to get the job metadata as shown here. So based on these start time and end time, and also the allocated nodes of this job, we can merge this information into the node level metrics. So after we inserted this job information, such as the job ID and also the step ID into this job level time series data, we can get the data that included the job information. So all these analyzed will be based on this job level monitoring data. So for the metrics we used in these the IIC paper, we mainly focusing on 4 metrics. For CPU only nodes, we have CPU utilization and the host memory utilization. And the GPU nodes, we include the GPU utilization, get through the DCGM, and also the GPU memory utilization. And as the time we collected the data for IIC, we do not have a memory bandwidth metrics. So this is our ongoing work. So we want to collect the memory bandwidth information for the Promata. And yeah, these 2 figures was showing in the IC paper. So as we can see, for both CPU nodes and GPU nodes, the maximum memory used by job is actually about 2/3 of the jobs use less than 50% of total memory capacity, which means the memory capacity is obviously underutilized. That's also the conclusion we presented in our previous paper. So another interesting information is the application information. And to get the application information, we use the a in-house tool developed at NERSC to analyze the job names. So these job names are actually specified in the job submission scripts, and we can get the job names through the saccount command. And this tool basically parses these job names and applies regular expression to identify these applications. As shown on this right figure, we can see that actually these regular expressions are manually defined. It is based on previous observations from the NERSC infrastructure. Therefore, this methodology cannot be used directly in other HPC sites. So together with the job metadata we collected and also the application informations, we can do some analysis like this. So for these decomposition of node hours by applications. So in the first row, we filtered jobs that is longer than 1 hour. And we decompose these node hours by applications. So these 2 figures were presented in the paper. And also we can change the threshold to like 6 hours to only focusing on these longer jobs for CPU and the GPU jobs. So through these figures, we can see that for GPU jobs and the ADLS application, the proportion of ADLS increased, mostly because of the Berkeley GW application is less than 6 hours. So this ADLS application, it's a percentage increase. And for the GPU jobs, we can see that, for example, the E3SM application, it's relatively short. So the percentage for the overlap quark propagator increase, and we can see some like difference if we change the threshold. So based on this data we collected through our code and the application information, we can do like similar analysis like this. So yeah, that's pretty much I have for you today. Yes.
Thanks. Sorry, one question. Sorry, thanks for presenting this because something new information that I have not seen in the paper. But one question I have for you, because you are saying node hours, right, by applications.
No, yes.
So my clarification, what we want to extract out is what jobs and maybe connected to the applications are taking more than say 6 hours, right? And it should be like 6 hours on one node, or it takes
Oh, no.
maybe 4 to 6 hours on multiple nodes, right? Because I am kind of saying maybe I'll sort of make a claim that will be the tougher applications that we look in more details to see if there is any opportunity to bring it, speed it up by say factor of 10x or something. So which
Okay,
applications? Yeah, go ahead.
So for this analyze, we basically focusing on the whole cluster utilization, and each application for each job, we only keep jobs running longer than 6 hours. We only focus on the long jobs in our analyze. So it's not like for each job, it will no matter how many nodes it use, the 6 hours is actually refers to the end time minus the start time. That's the threshold. It's not the cumulated node hours of these jobs.
Okay.
Yeah.
And how many nodes? So can you map this to the number of nodes it took? Because your paper shows that some jobs are taking more than 4 nodes or 16 nodes and all that, right? So
yeah, definitely we can do that. It's just not showing in these figures. We have this. We kind of have like a data frame, and we can add that kind of dimension in these figures. Yeah, we can do that.
Yeah, I mean, actually, yeah. I mean, realistically, what I'm trying to find out is basically which jobs are really consuming a lot of time, right? Start time and ascent time, right? So maybe there's a job that's like sitting at 12 hours, right? Because when you say greater than equal to 6 hours, you also done a histogram, right? Hey, does it take 10 or 12 hours? And that also takes lots of nodes. So that could be a prime candidate to kind of dive in and say, hey, what are the bottlenecks and how can you speed it up?
Right.
Can that be something that you can send it later on or send it offline? That just which applications are taking more hours and more nodes, or lots of hours and lots of nodes?
Yeah, sure. Definitely, I can do that kind of analyze. But again, so this data is actually kind of outdated. It's like collected about like 1 year ago, and also during that time, the promoter is not in full production mode. So we are trying to get some new data from the promoter now, and we are working on that. So do you want me to analyze based on this previous data, or probably on our later data?
Later data.
Okay.
Right. We would rather take the recent examples and try to see if we can find 1 or 2 applications that are really struggling for, say, hey, it takes a long time or lots of nodes. We would like hone in on that application and then kind of see how to kind of see where the bottlenecks are, right? Profile it. And that's the other thing we need to ask you, right? Once you do take, say, you can take the top 2 applications that take a long time, right? And say, hey, why is there a bottleneck? Is it a bottleneck for CPU, memory, IO, kernel, right? Then that'll give us insight to say, maybe that's the one we need to focus on.
You have to remember, we cannot profile this application though. We don't have the code, we don't have access to all that. And we can gain hints of what the bottleneck is based on some hardware counters. There's a hardware counter that talks about stall cycles because of memory. We're trying to get access to it. But we can't fully explain it. So that's why we were saying, like, we can use this data in a more fine, detailed form. But we have the data, it's just that the graphs were only showing like more than 6. Anyway, and then based on what is more popular, then we can go in and profile it. Even if we notice, for example, high memory bandwidth, that doesn't mean that the application was stalling because of it.
Well, yeah, no, let's get what, yeah, no, fair enough. If you can't get it, that's fine. I was like, kind of saw some of his charts they showed where the memory utilization and CPU utilization was shown in the, in the kind of slides before this. So maybe for that application that is taking a long time or consuming a lot of nodes, if there is also a way to even show the CPU utilization or the memory utilization, right? Whatever you can find, G, right? That'll just give us, add more color as to what is really is kind of slowing down to the extent possible. So if you can't do profiling, that's fine.
I think Sugu has his hand
Yeah.
up. Yeah.
So yeah, you mentioned that the metrics are accessed at a 10-second interval. 10 seconds is a long time to me. So I'm curious, is the metrics sampled once in 10 seconds, or is it like sampled in much more fine granularity, but then aggregated? I mean, what kind of data is there in that every 10-second interval?
Yeah, from my understanding, it is just a collect like every 10 seconds as of like last summer. So it's not like kind of for example, the average of the last 10 seconds. It's just the instantaneous readings at that moment.
So if there is a CPU utilization spike in the second, right? I mean, in the 10 seconds, if there is a spike, we will have all that information, correct?
No, we cannot capture the spike during this 10 seconds.
Wow.
So if it is possible that if we can like the actual data is higher or lower than the collected.
So
data,
we have only an aggregate.
We can capture the utilization, but we don't know if it was a big spike of 1 second or a smaller spike of 5 seconds, for example.
Yeah.
So we'll know, for
aggregate.
example, that it's not so every 10 seconds, LDMS goes in and reads the counters and puts them in a spreadsheet. What happened in between, it doesn't know how quickly the counter reads the new value. It just reads the new value.
Wow. Okay.
Yeah. But we I don't know like if they change the frequency for now. Probably they can increase the collecting frequency. Yeah.
I don't think so. I don't think so, because you got to remember there's a lot of data from many nodes, and it's already, we're talking about terabytes, multiple terabytes. So I don't think they're gonna change the frequency.
Okay.
So the counter could be implemented to kind of accumulate in that last 10 seconds instead of being like, the current sampling. That is definitely possible, right? Anyway, I think I got my answer.
I don't think that's no.
Okay.
Yeah.
Okay.
Rajesh.
Hi, nice presentation. Wanted to know what is the criteria in selecting the 10-second interval?
Actually, I don't know. They the NERSC guys they I don't know. They probably they're considering the data volume they're collecting, right? They have to provide a very large storage for this data. If we increase the monitoring frequency, that will be probably 10 times of the current storage. Yeah, that's their consideration. Yeah, we don't know. Yeah, but for these tools, they can actually configure to collect monitoring metrics every 1 second. Yeah, it is capable of doing that.
So there is a related question in the chat. I think it's very related. So do you capture the high watermarks every 10 seconds and reset for the next 10 seconds window? That should give some sense of peaks.
I don't think so. Like I said, from my understanding, they only get the instantaneous readings of that moment. Yeah.
Yeah, this is what I was actually meaning by saying aggregate. I don't know how the counters are implemented. If the IP implements the counter, then the counter will be aggregated. If the IP implements the memory utilization, then the memory utilization will be aggregated. So I don't know how the counter instead of just as a instant, a moment of sampling, versus if the counter kind of has some logic that it shows some kind of an aggregation, like an average or highest or something like that. But I don't know whether
it
I
does.
implement
It
like
does.
that.
It does.
It does.
So,
okay.
for instance, if you're talking about instructions executed, that is a like incrementing counter. Or the way we did memory bandwidth back in Core was by counting the cache misses. These are all counters that keep increasing when the event happens. So when you read it 10 seconds later, you'll count all the events. Of course, you know the time that has passed.
That really
So
helps.
you can sort of get the memory bandwidth in that 10 cycle window. Now, whether it was a big spike and nothing else, or I mean, you don't know the shape of what happened in between, but you know
Got it.
the volume of what happened.
Okay, that really helps. Thank you.
So I'm going to be the bad guy here, and I'm going to thank G for giving us this presentation. What I would suggest is maybe we can gather up all our questions and then try to send it to G and see if he can answer them later on. So I think we can do that together during the following week. So now we're going. Thank you so much.
Thank you.
We really appreciate it. So now we're going to go to Tom. So take it take it away.
Hello, so my name is Dor or Tom, whichever works best. So I have two first names, so whichever is easier, I go by that one. So I wasn't sure exactly how much detail to include in the presentation, so I tried to kind of keep it a little bit high level or something, or maybe like a discussion starter or something. So as Patricia said, so thank you so much for the introduction. So I've been working mostly on trying to accelerate DFT calculation, which is one of the big kind of like applications that's running on NERSC, for example. So, oh, sorry, something is not working. Okay. Just to kind of give an idea, so basically like density functional theory is kind of like a huge chunk of the NERSC workload. It's like, I think in a report from 2020, they're kind of saying that there was like 25% of the overall workload was spent in, for example, in doing DFT calculations. And I think in the presenter's previous talks, there were a couple of applications like VASP, Quantum Espresso, Qbox or something like that, which were actually applications that were done for this sort of calculation. So at the end of the day, DFT calculation is just kind of like an eigensolver. So you're given a system and you're trying to find the different kind of states of the electrons. The physics is going beyond my payday per se, because physics is not my strong point. But basically you're doing an eigensolver and you kind of like, it's an iterative process where you kind of try to find the minimum eigensolvers for a given system, eigensolutions for a system. So the whole thing can be expressed something like this. So the idea is you start with an initial guess of your wave functions, which basically are the things that they're going to describe, for example, the electrons. You're going to start computing this charge density. Then afterwards, in this step over here, you're going to actually do the computation you're going to compute your H, which is called the Hamiltonian. And finally, you're going to compute the Schrodinger's equation up to a certain point of convergence. Once you have a new solution for psi, you're going to repeat the whole process until some sort of parameters are satisfied. And for this sort of implementation, basically, there are multiple ways of doing it. So you have direct methods. So for example, Scalapack, EigenExa, and ELPA, they have already kind of like solutions to kind of do the whole problem in one shot. But the only thing is that these kind of methods, like direct methods, work very well if the system is small. But if you want to do a very large system, or let's say 1,000 atoms or 1,000 molecules of water, the direct method is going to be very inefficient. So that's where you have this whole process of going iterative. So instead of kind of like finding the solution in one shot, you kind of iterate multiple times through the computation to determine exactly like the solution. So you have Davidson, law PCG, conjugate gradient. Like these are some of the off-the-shelf algorithm that you can take from different libraries. And then there's also this thing called either you do a global minimization of the problem or you do a local minimization. So there's different ways of approximating the solution to actually kind of find the whole thing. So the thing that we're actually working with John Schall, for example, is based on this local minimization where it's called LS3DF. I forgot exactly what the actual expanded title is, but the idea is to kind of have a linear scaling of the computation. So the principle is that if you have a very big system, let's say 1,024 molecules of water, instead of solving the entire thing in kind of like the entire like eigensolver on the entire system, what you're going to do is you decompose this problem in subdomains, and you kind of come up with these kind of like small kind of tiles of the computation. And then basically you give these tiles to each of the processing nodes. They're going to be computed independently. And at some point you have to do a Poisson solver to kind of recombine all the solutions to form the entire kind of computation. So basically, if you can have a very efficient eigensolver implemented on a single node, then basically your computation can be done very efficiently. And then at some point you just have to do a global communication, and that's going to be the solution that you're going to have. Now, as I said, I'm talking about eigensolvers and kind of like a mixture of operations. So as I said, like the whole, like finding the minimum eigenvalues for a given system boils down to like an eigensolver. And the whole thing, for example, on this slide, I'm just focusing on the conjugate gradient approach. And basically, this whole computation is a mixture of linear algebra and Fourier transforms, because so the operation that we were looking at was more on plane wave DFT, which is kind of like working with frequency domain points. So that's why we have to use the Fourier transforms to kind of do the computation. So the calculation of these kind of like steps will require like three-dimensional FFTs. We'll have some pointwise scaling operations. There's also block sparsity. Apparently, it's a mixture of everything. So it's from dense. You have some of the operations that are going to be done in dense, while some of the operations are going to be done in sparse, right? So what we want to do is basically take this algorithm and as best as possible divide, kind of like come up with a solution, preferably a hardware solution, that we could accelerate the entire computation. Now, what we were, based on the stuff that we were working on, we kind of identify, well, I kind of cobbled also together, so some of the animations I might have forgotten about. But basically, what we kind of identified was that we looked through the entire application and we kind of identified this pattern appearing over and over again. So let me try to explain the pattern, and afterwards I'll go into a little bit more details. So what we noticed was that a lot of the computations are kind of centered around linear algebra operations, which are basically matrix multiplications. So usually we end up with like two gems that are going to be always back to back. But those gem operations are going to be always surrounded by kind of like pointwise operations or operations that are only applied in the columns, like Fourier transforms or scaling operations. So that's why I'm calling this kind of like, we have these specialized packing routines where we can actually do a Fourier transform, or we can actually do a pointwise multiplication. And basically all the computation that we see in the algorithm can be boiled down to like these sort of patterns. Now, of course, there's different flavors. So we identify three variants. There's a dense version. There's the version where I was talking about like there's an FFT plus a block sparse kind of like gem operation. And finally, there's another dense version, but it's used for orthogonalization. So what we are trying to do is basically come up with models to kind of predict what would be the performance and what would be like the design choices, like the parameters that to actually bake these things into hardware, and then simply cast the computation of the three regions of the algorithm on top of these guys. So for example, again, I didn't quite go into too many details because some of the stuff is also ongoing work, but it's also, I wasn't sure exactly how much detail to provide here. So I just kind of give a couple of highlights. So for example, these are
those three patterns, sorry, go back on those three patterns, are they set at the job level or the application level?
So these are in the algorithm itself, in the solver.
Okay.
So those three patterns appear in the algorithm, like in the innermost loop. So the one that's going to be the most time consuming.
Okay, got it. Thank you.
Right. So all three of them, specifically for this application, specifically for this application and for this algorithm, all three patterns can be identified within the code. So for example, this is one of the patterns. Like for example, in here I have like from line 2 to line 7. This operation just kind of does like a pointwise scaling, like for each. So everything is, imagine you have a 2D matrix. You're taking, so the B dimension is going to be in the columns. And basically what you're trying to do is for each of the columns, you're doing some sort of operation. So basically you're doing a dot product followed by an AXP operation, and then you're scaling something. And again, you're doing some AXP operation. So basically this whole thing can become a packing routine where we can simply, as we stream the data from memory, we can do this operation and pack it for the buffers for the gem. And this one fits nicely because 8 and 9 are exactly the two gem operations, which are going to be the projections. And finally, we also have FFTs. So Fourier transforms, because a lot of some of the operations are going to be done in real space, some of the operations are going to be done in complex space. But we can actually, because we do a 3D FFT, the 3D FFT can be separable. So we can actually shove one of the FFTs actually as an unpacking routine. As the result comes out, we can actually transform it back into frequencies. We transform it partially, and we simply push it to main memory. So as long as we actually can hide that latency. So right now what we're working is coming up with exactly the configuration where we can actually hide the latency and the data movement from DRAM. As I said, this one is, so that was one of the patterns. This one is similar to that pattern. We also have again, all the other 2D FFTs that we have to compute, plus some block sparse operations as well. And this one we actually did in software. So this was a paper from 2021, where we actually took this entire computation and we remapped it and actually executed, for example, on a CPU and on a GPU. And we showed, for example, performance improvement. So for example, in this plot, what we're showing, so this is, I think we were showing relative performance with the baseline. So we took the baseline as the classic library implementation that's being used, for example, in a lot of these codes. And then we did a couple of things. So, so first we had an optimized implementation where we just optimized the libraries in isolation. So we optimized the FFT library, we optimized the block sparse library, and that one provided us, for example, like a 2x, 3x improvement over the baseline implementation. But then we also kind of, by reshaping the computation and kind of mapping it into this kind of like, I would say, well, John was kind of like data flow kind of thing, where data goes from the FFT to the gem unit and afterwards back to the gem unit and so on and so forth. So that's kind of like a data flows through these computational units. On top of that, we also achieved almost like an 8x improvement over the baseline implementation. So we managed to reduce data movement and keep it as much as possible in cache. So, oh, I forgot to say, so on the x-axis is just, there's a lot of numbers, but basically there are different configurations. Like, for example, FFT size, how many columns do we have, and how many of these block sparse projectors, because some of the data sets are going to be block sparse. Now, we also did, for example, we moved it, for example, to like a bigger system, so an AMD EPYC processor. And here again, on the x-axis, we're showing, for example, the different configurations. Y-axis is going to be the relative performance. Higher is going to be better. Blue is the baseline, as I said, and then the red part is going to be the one where we actually provide benefits. So, so for some of the small sizes here, we actually messed up something in the configuration, because we had to do like a lot of synchronization points. And when we had to cross the link between the two CPUs, that was miserable. So that's why the performance is not exactly great. But as the problem size increased, we actually managed to get almost 12x improvement over the previous implementation, like the baseline implementation, by using this data flow approach. And finally, we also tried to kind of push it on the GPU. Unfortunately, on the GPU, we don't have enough buffers, because the shared memory on an NVIDIA GPU is going to be like, what, 96 kilobytes. So in order for you to kind of regroup the computation and kind of push the data from from the FFT to the gem, you do require some buffers, and those buffers may actually be a little bit larger than what the shared memory can offer. So we only show like at most a 2x improvement over the baseline implementation. And finally,
go back one to your number of sockets.
Yeah.
I said this one you're saying 2, 32, and 64 sockets.
Yeah.
Sockets cores. So this is definitely a cluster, small HPC cluster.
So this is a single node on Perlmutter. So it's a 2 EPYC processors. So you have these two. So everything is on a shared memory system. So these are going to be 2 socket systems on a single node on Perlmutter. Yeah.
No, but then you got 64 sockets, right?
Sorry, no. So 2 sockets, 32 cores, 64 threads.
64 threads. Okay, sorry.
Yeah. Sorry, my bad. It's like the notation. I might have messed it up. But
yeah. Okay.
Yeah.
So
you're able,
yeah.
Yeah.
So it's pretty interesting, because you're able to get almost 12x improvement over the baseline just by changing the FFT size, batch size, and number of projectors.
It's not only the changing the dimensions. It's also so there are some correlations between as the problem size increases, because the amount of data that you actually can fit on the CPU on a single node, so as the FFT increases, the number of columns that you have to store will start decreasing. So that's actually going to be, that's why we're actually seeing different performance improvements when we change the dimensions.
Yeah.
Because in some cases, it's going to be the memory access patterns are going to be not exactly favorable as the number of columns decreases. So that's going to be that's going to cause problems for the baseline implementation.
Yeah, and it's very well done, actually. Very well done.
Right. Yeah. So basically, yeah. So and then finally, what we're trying to do right now is we're trying to use the same kind of pattern, this kind of pack, unpack, two gem operations for the orthogonalization step. So that's an ongoing work right now. I don't have any numbers for it, but the main story that I wanted to kind of show with this is that we kind of identify a key pattern that appears within the application, but it has some flavors, right? So it's not just going to be dense, it's going to be block sparse, but it's also going to be utilized in more complex linear algebra computations. So what we're trying to do is, while we have the software implementation, we showed performance gains, I think by simply kind of like focusing on trying to build like custom hardware for some of these guys and maybe put them as chiplets or something like that in like an AMD processor, I think moving forward, that would give us a little bit more benefit for the entire application. So that's what we're trying to do right now. And again, I didn't put so much numbers because it's still ongoing work, but hopefully soon we'll have some numbers and I can share them as well with you guys as well. So yeah, but also I wasn't sure how much details to go into. So, but yeah, that's about it. That's kind of like the presentation that I want to talk about.
So is there any opportunity to go back to your slide that shows 12x improvement? So here, let's take one, right?
Right.
12x improvement, your 128 FFT size, 256 batch size. And let's say for these,
yeah,
going from, so what you're trying to do is to see if there's any modular architectures we can build that gives like 10x
yes,
or 20x more performance improvement, right?
More. So on top of
the question is, yeah, on top of this, the question is,
so on top of this thing, we are still using, so because again, we are using the L3 cache as the buffer where the FFT kind of loads the data and pushes it into the L3, and then the gem takes it from there and kind of like starts computation. However, if you were to kind of remove that part and just kind of like push, what do you call it? You push the data through from the FFT to the gem and kind of remove the L3 cache, based on the numbers that we were seeing, we should be able to see another 2 or 3x improvement over the software implementation if we were to have it built in hardware.
Good. Okay, good. No, that is a good, no, that's a good, good direction for us to have. Okay.
So the whole thing right now, because of the system, so the system that we are running at, another comparison we did was also if we actually streaming the data as best as possible from DRAM, right? So right now, our implementation in software is achieving almost 100 gigabytes per second. So we're still 50% from the peak performance of the system itself. So again, I think like if we were to kind of like also stream the computation and do some other tricks as well, we could be able to move the computation at the bandwidth bound, like the peak bandwidth that we can achieve. So there's still room for improvement. And I think a lot of the inefficiencies are going to come because we have to take the data to the CPU, push it to the L3 cache, and then afterwards take it from L3 cache and move it back and forth between the cores. So I think that's an inefficiency.
Great observation. No, thanks for that. And you guys already planning the next step, or is it just something that we could be looking at in this forum?
So we are working right now on modeling the hardware and how it should look like. And so one of the things that I didn't introduce in the presentation was the modeling aspect of how do we actually, what are the design choices for the different FFTs, the different point cloud operations in linear algebra. So that's what we're working right now. So we would love to kind of show the results once we have them and take it from there and see, hey, does it make sense to kind of be actually building like chiplets or something for this sort of computation? That's something interesting.
That'll be awesome. The modeling, which model tool are you using?
So this is, well, modeling as in we are literally modeling by hand, creating the formulas, saying exactly, okay, how is the, what do you call, literally kind of having like a spreadsheet to say, okay, what are the parameters that we need? How many parallel units do we have? How many like FMAs do we need, and so on and so forth? What's the bandwidth for that? What's the temporary buffer? So we literally have a spreadsheet where we put all of these numbers. So it's not exactly like an automated step. It's more of a like, okay, let's start from basics. Try to kind of implement the kernels and the microkernels of the FFT, linear algebra, and block sparse computation, and build on top of those to actually build like a bigger model for the whole computation.
Got it. Okay. All right. Thank you.
Yep.
One interesting part of Doru's work is at the end of his journey, he might have a really good idea of how the processing chiplets will look like for this particular problem, right? So one of the questions we would love to answer in this work stream is what other chiplets these processing units would need in order to create the modular system, right? Because let's say at the end of Doru's exploration, he will say, okay, we're gonna need to have a gem chiplet, right? We're gonna have to have a TSQR chiplet, or we're gonna have to combine them both in a single chiplet. We're gonna have this amount of memory. But then what other chiplets do we need to actually being able to put this into a modular system? So there are some questions on the chat. So what makes 128, 512, and 256 drops to 10 times versus 12 times, Tom?
Oh, yeah, so as I said, like so imagine you have a matrix. That's what so one of the dimensions, the number of rows, is going to be basically the FFT size, which is going to be, let's say 128, but it's a 3D FFT, so it's going to be 128 cube. And then you have the number of bands is the number of columns, right? So on a single node, because again, we were focusing on a single node computation, you have finite DRAM. So as the FFT dimension increases, so for example, you go from 128 to 256 to 512, the number of columns decreases. So that may not be beneficial for the classical implementation, but for our implementation, because we're actually keeping more data on chip and we don't have to kind of bite the bullet of accessing, like having bad access patterns, I think that's where the 10 to 12x is going to increase. So it's not that our implementation is going to go better, it's just that the baseline implementation is going to go worse. Does that answer your question?
Well, a lot of people are nodding. Yeah.
I think it might be good to see when you get your next round, Doru, we'd love to see how you're modeling it in a simple way. So we may want to see that kind of that sensitivity analysis.
So I'll
Right.
once, as I said, like once I have like we have the things in place, I don't mind sharing those results as well and seeing how the actual thing. So even the software implementation, we had a small model, but it was not very like accurate. So we're trying to improve that one as well. So yeah.
And maybe it is worth to clarify that the modeling that you're doing right now is on the hardware accelerators, not on the many core system. So this is actually hardware accelerators that are being built using some hardware description language. So that's what makes the modeling a little bit more challenging.
Right.
No, hold on, Forrest. I just thought all of this is being done on that AMD.
So this is on the software side. So, but the chiplet part is literally like the chiplet part. We're building the hardware itself as well.
Okay.
So,
Okay, you are. Okay. You're building the hardware. Okay.
Yes.
All right. So, okay, good. Maybe good. At some point, maybe share how you guys are building the blocks out there, right?
Yep.
Okay, cool.
The way I'm understanding is when we decompose a problem, just because we are increasing the factor will not yield more performance. It should be more aligned to the model of the solution we are using, right? So yeah, thank you.
Yes, so I guess it's also worth clarifying that Tom presented like 2 steps, right? So the first one is the first approach where he did everything in software with the technology that were available at the time. So also just to clarify, so Tom, if you have a link to the paper, you
oh yeah, sure.
Yeah, so that would be people are asking for it. And then the second, like I guess the second part of the work, that is the part that is ongoing, that is actually very exciting to us, is the fact that he's actually building hardware for this, and he's trying to figure out what is the most efficient way of building this hardware.
And in building this hardware, building this hardware, this is where you might say, hey, look, I don't need an L2 cache. I can just directly flow the data in.
Right.
So okay, all right. Okay, that's
right,
what you're already planning for that. Okay.
Yeah, so we do have some of the microkernels for the gems and the FFTs and like the pointwise operations and TSQRs and stuff like that. We do have some tiny chisel generators. And so Mario, who's been working with me for the last 2 years, so he's been developing this. And we've been kind of like, we've been trying to use some of the other tools, but we ended up with because of the problem sizes, we actually had to go and build our own things. So hopefully he can, well, Mario can actually release some of the software, like the Chiplet implementations as well, to generate these kernels. So yeah.
So when you say building the hardware, are you talking about creating the models?
So we have two things. One is going to be the tools to generate these kernels, and then the models we're also building the models themselves to kind of understand how to link these kernels, right? Because in the application itself, you do want to kind of stream the data from one unit to the other, but then at what granularity? What are the constraints that you want you're going to have? Like maybe like you don't have enough memory on chip or something to actually stream at that rate. So yeah.
Thank you.
Okay, so are there, I mean, if there are not more questions.
I'm just curious, one question, I'm just curious. So how are you creating these models? I mean, what platform are you using to create these models, if I may ask?
Microsoft Excel.
Wow, okay, thank you.
So
sorry. So the thing was, so it's kind of like I start like basically it's kind of like coming up with the equations that will tell me, okay, what's the latency, what's the throughput,
Got it.
And then kind of parameterizing those equations like by how many parallel units do I want to do, like in the different, like if it's a 2D matrix multiplication. That's what I'm referring by modeling. It's like literally putting together the equations.
Thank you.
okay.
So at the end of the day, if basically what we noticed was that if we have all the equations for the computation, it becomes a minimization problem. So if we feed it, for example, like into like a linear like Z3 solver or something, it will actually provide us some information and say, hey, is it solvable or not? So it will try to kind of give us a solution if we're going on the correct path. So that's what we're trying to do. So I hope that answers the question.
And you started with GEM, right? Because that y'all may basically through some other analysis felt would be the one where the most kind of
right. So
bottleneck, right?
Right.
Many
So
HPC, right?
Right. So the GEM is going to be the main unit, but then because of the surrounding computation, you have a lot of like FFTs or linear operations that are not that consuming. And also you may have also block sparsity. So that's another thing. So you want to pack the data in a correct shape so that you don't actually like do computations with zeros or something. So it's those packing routines become really important because yeah, you can build efficient GEMs, but feeding the GEM units is going to be tricky.
No, my question is, you all started with GEM instead of say versus some other HPC kernels. Any reason, any particular reason why you started with GEM versus any other HPC kernels?
So the reason was because it was the predominant kernel in the algorithm that we were looking at.
Okay. Okay, and you all not have done any study on say other HPC kernels like Stencil or
not right now. Not right now.
Okay.
Not right now.
Not right
No,
now.
no,
Okay.
no,
All
no,
right.
no.
Okay. Thanks.
That would be the next
Yeah.
steps. Like this was one of the applications that had this nice mixture of dense linear algebra, matrix multiply, block sparse linear algebra, FFTs, and like pointwise operations. So it was just this mixture. It would have been interesting to have stencils as well, but that one, thank God, is not in there yet.
Sorry, what was the name of the application? I think I might have missed it. What is the name of the application?
So the application, so this is a density functional theory solver. So it's a conjugate gradient that's seen in a lot of software like VASP or QBox or Quantum Espresso. So those three are the main software that are being utilized by people, for example, at NERSC to do DFT calculations. So conjugate gradient, conjugate gradient is one of the kind of like the workhorses for these kind of solution for these computations. So we just picked that one and we focused on the plane wave DFTs because of the mixture of different components.
Okay.
Well, thank you, Tom, for your talk. We really appreciate it. We might gather some questions and send an email to you with questions.
Sure, I don't mind. Just send them over. I'll try my best to answer or confuse you guys, one of the above.
Thank you so much. And then for everyone, just a reminder that if you guys have useful links to kind of create a baseline of how chiplets are done today, I would appreciate if you send it my way. You know, information, everything that is open out there that you can help me with to create this kind of baseline of state of the art. I would really, really appreciate that. And don't forget, in the next meeting, we have Anna that is going to talk about artificial intelligence kernels. So that's also going to kind of complete the whole vision that we have for this work stream. So thank you, everyone, and see you next time.
Thank you.
Thanks all.